Hello and welcome to Introductory Astronomy. In this course, we're going to cover stellar evolution and cosmology. And before we jump to that, we're going to start by covering the basics in astronomy. Therefore, the chapters covered will be chapters 1 through 4 and 16 through 27 of the textbook Astronomy Today by Chaisson and McMillan. Please make sure you go online and you register for the Mastering Astronomy course that is attached to this class. You're going to be seeing a lot of Mastering Astronomy icons throughout your textbook. And if you click on those, they will direct you to related animations, videos, and interactive figures in the Mastering Astronomy website. So they're very useful. You will also find all your homeworks and quizzes and exams on the Mastering Astronomy website. So it is essential you log in there as soon as you can. Now, taking a look at this picture right here, starting with chapter 1, high overhead on a clear, dark night, we can actually see a rich band of stars, which we call the Milky Way. All these stars, and a lot more, are part of a much larger grouping of stars called the Milky Way galaxy, of which our star, the Sun, is one member. The single exposure, called the Going to the Stars Road, was made at night with only the moon's light illuminating the terrain on the Continental Divide at Logan Pass in Glacier National Park near the Montana-Alberta border. Now, just like Lao Tse said, the longest journey begins with a single step. So we're going to go ahead and start with our basics of chapter 1. We're going to begin our journey in astronomy by talking about our place in space. Where are we located? We're going to talk a little bit about scientific theory and the scientific method because astronomy is a science. Then we're going to move on to angular measure, which is going to be very useful in giving us the sizes of celestial objects. We're going to move on to a basic description of Earth's orbital motion. And from there, we're going to jump to the motion of the moon. And finally, how to measure distances using basic geometry and trigonometry. So where are we? We are located on planet Earth, which is the third planet from the Sun in our solar system. We don't particularly occupy any special place in the universe, unlike what our ancestors believed. And our planet is mostly a solid object, although it has some liquid in its oceans and core and gas in the atmosphere. In this view, it is a NASA picture that shows the North and South American continents and a big part of the Pacific waters. Now notice on the lower right side of this picture, we see what we call a full spectrum icon. If you take a look, it looks like a little wave wiggling through. Starting from the left side, that is radio wave, which is the longest wavelength, and it gets smaller moving towards the right side, going to infrared, visible, ultraviolet, X-ray, and ending up with gamma rays, which have the smallest wavelength. Throughout the textbook, you're going to be seeing images taking at different wavelengths, and they will be supplementing the visible light images. And this is a very useful tool for astronomers because it helps us exploit the full range of the electromagnetic spectrum when gathering information about the cosmos. In this particular picture right here, notice how the letter V is highlighted red. This is telling us that this picture was taken in the visible wavelength. So we are on planet Earth, and planet Earth is part of the universe. So a good question would be, what is the universe? And simply put, it is everything. The totality of all space, time, matter, and energy. Pretty much everything. Astronomy is the science that studies the universe. One very important thing I'd like to mention about astronomy is that because it deals with the whole universe, it deals with scales that are incredibly large. We're talking about distances that are very, very, very big. So throughout this course, we're going to introduce several units to explain and describe these large distances. The first one I'll mention, which you probably have heard of already, is called the light year. And unlike the name implies, a light year is not a unit of time, but it is a unit of distance. Simply put, it is the distance light travels in a year, which corresponds to about 10 trillion miles. So that is a very, very incredibly large distance to cover. I want to draw your attention to the picture on the right. It is a size and scale picture. The bottom of this figure shows a spacecraft and astronauts in Earth orbit. And then we see a view that widens progressively in each of the next 5 cubes drawn from bottom to top. We have Earth, then our planetary system, the local neighborhood of stars, followed by the Milky Way galaxy itself, and the closest cluster of galaxies. Finally, the image at the top right shows the spread of galaxies, which are represented now as white dots, the spread of galaxies in the universe on extremely large scales. The field of view in this final frame is hundreds of millions of light years across. And remember, 1 light year is 10 trillion miles. The numbers showing on the picture indicate approximately the increase in scale between successive images. Starting from the bottom, Earth is 500,000 times larger than the spacecraft in the foreground. The solar system in turn is some million times larger than Earth. The local stellar neighborhood is 10,000 times larger than the solar system, and so on and so forth. If you notice, I put a link on the lower left. It is a video. It's about 10 minutes long, and it's called Powers of 10. It is a 1968 American documentary written and directed by Ray Ames and her husband Charles Ames, and re-released in 1977. This film I find incredibly useful. It depicts the relative scale of the universe in factors of 10. This video will take you on an adventure in magnitudes. Starting at a picnic by the lakeside in Chicago, it transports you to the outer edges of the universe. Every 10 seconds, you will view the starting point from 10 times further out until our own galaxy is visible only as a speck of light among many others. Then you will return to Earth with breathtaking speed, moving inwards, into the hand of the sleeping picnicker, with 10 times more magnification every 10 seconds. Our journey will end inside a proton of a carbon atom within a DNA molecule in a white blood cell. This video really puts into perspective the idea of sizes, and I would definitely recommend it because it will help you visualize what's taking place. Here we have a picture of a typical spiral galaxy, which is a collection of about 100 billion stars, each separated by vast regions of nearly empty space. Our sun, our star, is a rather undistinguished star near the edge of another similar galaxy called the Milky Way galaxy. Now, this picture was also taken by NASA, and notice on the bottom right, it was taken by visible wavelength. Another thing I want to point out here is that this galaxy is about 100,000 light years across. 100,000 written in scientific notation in powers of 10 would be 10 to the fifth. So the way to remember that, the little trick for that, the number 100,000 is 1 followed by 5 zeros, so you just write it down as 10 to the fifth. If you want a refresher on powers of 10 in the scientific notation, see Appendix 1 in your textbook, and also the math review file that I have put online. Now, in order to avoid large numbers beyond our imagination, due to the vastness of the universe, we introduce new units. One very important unit is called the astronomical unit, which is written in capital A and U. Now, one astronomical unit is equivalent to 150 million kilometers. And million corresponds to 10 to the 6. Now, this distance is very special because by definition is the distance from the Earth to the Sun. So here's a picture right here depicting the Sun on the top right and the Earth on the bottom left, and the distance between the two is labeled 1 AU. Now, to compare that to 1 light year, which we mentioned earlier, 1 light year is 10 to the 13 kilometers. 1 AU is 150 times 10 to the 6 kilometers. So 1 AU is a lot smaller than 1 light year. In fact, that makes sense since it takes light about 8 minutes to reach us from the Sun to the Earth, which is nowhere close to 1 full year. The inset on the bottom right shows the relative size of the Sun and the Earth. So that was our brief introduction. I would like to talk about the scientific theory and the scientific method. Scientific theories must follow these 4 criteria. They must be testable, they should be continually tested, and should be simple and elegant. Now, when we say elegant, we mean mathematically elegant. It should not be this incredibly complicated, convoluted explanation for what we observe. But as usual, the simplest answer is usually the correct one. So as scientists, we always strive towards a simple, elegant solution. Scientific theories can be proven wrong, but they can never be proven right with 100% certainty. So how do we come up with theories? Well, first we observe a phenomenon, and we come up with an explanation that we think explains what is taking place. Then that theory, if it is correct, should lead to predictions that are consistent with the previous observations and any follow-up observations. So scientific theories evolve through a combination of observation, theoretical reasoning, and prediction, which in turn suggests new observations. This process can begin at any point in the cycle shown on the slide, and it continues forever, or until, of course, the theory fails to explain an observation or makes a demonstrably false prediction. And what happens in that case, we discard the theory and we come up with a new one, and the whole cyclic process starts over again. Facts. Facts are the things we observe and measure, as opposed to opinions or ideas. Theory is our explanations of those observations. And science is the cyclic process that never ends. Science in general provides us the opportunity to enhance our understanding of the world around us. Physics, for example, strives to explain how everything works. Astronomy tries to explain where we came from and where are we going. Let's take a look at the obvious view. When we look up in the sky, our simplest observation at night in the sky. Usually we can see, if it's not cloudy, about 3,000 or so stars at any one time. Now, these stars are distributed randomly, but the human mind in general tends to find patterns in what we see. The picture on the right, which was taken with visible light, shows the constellation Orion. Another name for that is designation M42. That is a photograph of the bright stars that make up this constellation. This whole constellation concept started with our ancestors, who grouped the stars together in figures that had some sort of meaning in their mythology and history. Now, the constellation Orion was visualized by the Greeks as a pattern of a hunter. You can easily find Orion in the northern winter sky by identifying the line of 3 bright stars in the hunter's belt, labeled Delta, Epsilon, and Zeta. The Greek letters themselves serve to identify the brightest stars in the constellation, starting with Alpha, corresponding to the brightest star, Beta, the second brightest, Gamma, the third, and so on and so forth. The Greek alphabet is in your textbook. Now, in terms of the constellation, most of them are not very useful. But there is one star that is very useful. That star we call Polaris. And it is useful because it points almost due north. So locating the constellation that Polaris is located in, and in fact the asterism that has Polaris, is useful in pointing out north. And in a couple of slides, I will show you how to do that. What is absolutely useless is what we call astrology, which makes predictions about individuals based on the star patterns at their time of birth. Astrology is not a science, and please do not confuse with astronomy. There are 88 official constellations with clearly defined boundaries. Of these ancient constellations, 48 are still in use. Now remember, constellations are meaningless, but they can be convenient in terms of pointing you in a direction in the sky. Here are some of the popular ones. The most well-known Orion on the bottom here, that with a little bit of imagination looks like a hunter. Constellation Gemini, Canis Major, Taurus, and so on and so forth. This is not a class that emphasizes the memorization of constellations and their brightest stars. If you're interested in that, there's nothing keeping you from memorizing all this, but I will not ask you to do that in this class. You can always look them up in a star chart. Now, here is really what is taking place when we look in the sky and we think we see what the ancients Greek called the pattern of a hunter, the constellation Orion. So stars that appear close in the sky are not necessarily close together in space. So here is what we see projected in the sky that looks like the hunter, but in reality, here are the true locations of the stars that make up this constellation. So you can see why we talk about constellations being meaningless, because the true location of the stars may not be anywhere near each other. So this is the true three-dimensional relationship among the most prominent stars in Orion. And notice how some of them are 1,000 light years away from us. Remember, 1,000 light years means this is the distance that light travels in 1,000 years. Here are some easily recognizable constellations and their brightest stars. Right here we have constellation Lyra and the bright star Vega. Over here is the familiar Orion, and Betelgeuse and Rigel are the brightest stars there. I would like to talk a little bit about Polaris. And when we're figuring out the location of Polaris, we use what's called the Big Dipper and Little Dipper. The Big Dipper looks like a kettle pot, and if you see this up in the sky and you take a look at the edge of the pot, those two stars right there, and you draw a line in that direction, headed up, but you may not be quite sure where you're headed if you chose the right two stars, well, Polaris would be at the end of what we call the Little Dipper. So you should be able to identify between these two asterisms. And Polaris points pretty much north. Now, when we're trying to locate things in the sky, it is very, very useful to think of this imaginary sphere encompassing the Earth. This imaginary sphere we call the celestial sphere. Notice how our planet, our location, is sitting fixed in the center of the celestial sphere. And the celestial sphere can be made as big as we like, so it can contain all the stars that we see. This is one of the simplest possible models of the universe, but it doesn't agree with all the facts that we know about the universe, but it helps us visualize what's taking place. Now, the eastward rotation of the Earth causes the sun, moon, and stars to move westward in the sky, as if the celestial sphere was rotating westward around the Earth. From any location on the Earth, you see only half of the celestial sphere, the half above the horizon. What we call the zenith marks the top of the sky above your head, and the nadir marks the bottom of the sky directly under your feet. The drawing over here of the celestial sphere shows the view for an observer in North America. An observer in South America would have a dramatically different horizon, zenith, and nadir, an essentially view of the sky. The apparent pivot points of the celestial sphere are the north celestial pole and the south celestial pole, located directly above the Earth's north and south poles. Halfway between the celestial poles lies the celestial equator. Earth's rotation defines the directions you use every day. The north point and south point are the points on the horizon closest to the celestial poles. The east point and the west point lie halfway between the north and south points. The celestial equator always touches the horizon at the east and west points. Now, stars seem to be projected lying on this inner surface of the celestial sphere that surrounds the Earth. Of course, they aren't, but we're using this model of two-dimensional coordinates to help us locate objects in the sky. The apparent motion of the stars, I'm saying apparent to differentiate it from true or real motion, the apparent motion of the stars is the result of the rotation of the Earth and not of the celestial sphere. Constellations seem to move across the sky from east to west. They seem to move, so there is an apparent motion of the stars. And again, this is due to the rotation of the Earth. So now we have this imaginary celestial sphere that encompasses all the stars. And when we look up in the sky, we want to figure out how big those stars or whatever objects we're looking at, how big they are. And in order to do that, we want to talk a little bit about some basic math. So here's a little refresher course right here. We know that a full circle contains 360 degrees. And if we divide the circle into 360, then we get 1 degree right here. Each degree in itself can be broken into 60 parts, which we call arc minutes. So if we take this right here and we break it into 60 parts and we zoom in, we have 1 degree, and that's the symbol for degree, is equal to 60, that's the symbol for the arc minutes. Each arc minute in turn can be broken into 60 more pieces, which we call arc seconds. So 1 arc minute contains 60 arc seconds. This is very useful because the angular size of an object depends on its real size and distance from the viewer. So if we can relate the three, we should be able to figure out how far away the stars really are. So you might hear astronomers say the star was only 2 degrees from the moon. Of course, the stars are much further away than the moon, but when you think of the celestial sphere, you can measure distances on the sky as angular distances in degrees, arc minutes, and arc seconds. Again, an arc minute is 1/60th of a degree, and an arc second is 1/60th of a minute of arc. Using that, the angular diameter of an object is the angular distance from one edge to the other. Let's put this together. If you're the observer right here, and you're looking at a distant object, perhaps a star, you can measure the angular diameter, and if you know the distance, you can figure out the true diameter of the object. There's a nice mathematical relationship that relates the three. The true diameter of the object is equal to its distance, how far away it is from us, times its angular diameter. And when you use this formula, you have to use the units of not degrees, but radians. 360 degrees is equal to 2 pi radians. Now, what is the moon's angular diameter? If you stretch out your hand totally straight in front of you and you go outside late at night and you pull out your pinky should be able to cover the whole moon. And that corresponds to half a degree, which is 30 arc minutes. Now, both the sun and moon are each about half a degree in diameter, and the bowl of the Big Dipper is about 10 degrees wide. In order to distinguish these units from the similarly named units of time, astronomers refer to small angles in arc minutes or arc seconds. So the word arc indicates that the numbers refer to angles and not time. Let's talk a little bit about the Earth's orbital motion. I want to talk about the distinction between a solar and a sidereal day. A sidereal day is the Earth's true rotation period, the time taken for our planet to return to the same orientation in space relative to the distant stars. A solar day is the time from one noon to the next. The difference in length between the two is easily explained once we understand that the Earth revolves around the Sun at the same time as it rotates on its axis. Frames A and B illustrated here are one sidereal day apart. During that time, Earth rotates exactly once on its axis and also moves a little in its solar orbit, about 1 degree. Consequently, between noon at point A on one day and noon at the same point the next day, Earth has actually rotated through 361 degrees as shown in frame C, and the solar day exceeds the sidereal day by about 4 minutes. Now, these diagrams are not drawn to scale. The true 1 degree angle is in reality much smaller than shown here, but this illustrates the point very clearly. I want to talk a little bit about seasonal changes. This figure right here, if you take a look at frame A first, illustrates the major stars visible from most locations in the United States on a clear summer evening. The brightest stars, Vega, Deneb, and Altair, form a triangle high above the constellations Sagittarius and Capricornus, which are low on the southern horizon. If you take a look at frame B, though, in the winter sky, these stars are replaced by several other well-known constellations, such as Orion, Gemini, and Leo. In the constellation Canis Major lies Sirius, or the dog star. It is the brightest star in the sky. Year after year, the same stars and constellations return, each in its proper season. Every winter evening, Orion is high overhead. Every summer, it is gone. These regular seasonal changes occur because of Earth's revolution around the Sun. Earth's darkened hemisphere faces in a slightly different direction in space each evening. The change in direction is only about 1 degree per night, too small to be easily noticed with the naked eye from one evening to the next, but clearly noticeable over the course of weeks and months. And this can clearly be illustrated in this figure right here. This is what we call the zodiac. The view of the night sky changes as Earth moves in its orbit about the Sun. And as drawn here, the night side of Earth faces a different set of constellation at different times of the year. The 12 constellations named in the picture make up the astrological zodiac. The arrows indicate the most prominent zodiacal constellations in the night sky at various times of the year. For example, in June, when the Sun is in Gemini, Sagittarius and Copernicus are visible at night. Now, what is ecliptic? Ecliptic is the plane of Earth's path around the Sun. And it is at 23.5 degrees to the celestial equator. This picture right here illustrates the seasons. In reality, the Sun's apparent motion along this ecliptic is a consequence of Earth's orbital motion around the Sun. The seasons result from the inclination of our planet's rotation axis with respect to its orbit plane. The summer solstice corresponds to the point on Earth's orbit where our planet's north pole points most nearly toward the Sun. The opposite is true of the winter solstice. The vernal and autumnal equinoxes correspond to the points in Earth's orbit where our planet's axis is perpendicular to the line joining Earth and the Sun. The insets in this picture show how rays of sunlight striking the ground at an angle, for example, during northern winter, are spread over a larger area than rays coming nearly straight down during the northern summer, for example. As a result, the amount of solar heat delivered to a given area of Earth's surface is greatest when the Sun is high in the sky. So what is truly causing the seasons is the Earth's axis of rotation, which is tilted by 23.5 degrees to the true perpendicular to the plane of the Earth's orbit. This is the true cause of the seasons. So I'd like you to think about it in a sense of the variation of angle of incidence of the sun's rays. So if we take the two extreme examples, at summer solstice, the longest day, if you follow the path of the sun along the sky, we will receive more energy when it is shining on the Earth's surface under a steeper angle of incidence. And notice how the path that the sun has to travel is longer. It will be up in the sky for a longer time. On the other hand, at winter solstice, the shortest day of the year, the path of the sun in the sky is shorter and the angle of incidence is smaller. So the amount of heat energy that is received from the sun during winter solstice is minimized. There's a common misconception that the Earth's distance from the sun influences the seasons. However, the Earth's distance has a very, very minor influence on that. Here is a small animation, and you can see that this is greatly exaggerated. The Earth in January is actually closer to the sun than it is in July. Therefore, the true cause of the seasons is just the tilt of the axis of rotation of the Earth, that 23.5 degrees. Now, Earth has many motions. It spins on its own axis, it travels around the sun, and it moves with the sun through our galaxy. We have just seen how some of these motions can account for the changing nighttime sky and the changing seasons. In reality, the situation is even more complicated. Like a spinning top that rotates rapidly on its own axis, while that axis slowly revolves about the vertical, Earth's axis changes its direction over the course of time. But keep in mind the angle between the axis and a line perpendicular to the plane of the ecliptic always remains close to 23.5 degrees. If you take a look at frame A, it illustrates this motion. This change is called precession. It is caused by torques, twisting forces on the Earth due to the gravitational pulls of the moon and the sun, which affect our planet in much the same way as the torque due to Earth's own gravity affects a top. During a complete cycle of precession, about 26,000 years, Earth's axis traces out a cone. Right now, the Earth's axis is pointing nearly toward the star Polaris. In about 12,000 years from today, we will be almost halfway through one cycle of precession, and the Earth's axis will point toward a star called Vega. And at that time, that will be the North Star. 5,000 years ago, the North Star was a star named Thuban in the constellation Draco. The time required for Earth to complete exactly one orbit around the Sun relative to the stars is called a sidereal year, similar to the sidereal day. Now, one sidereal year is 365.256 mean solar days long, about 20 minutes longer than a tropical year. The reason for this slight difference is Earth's precession. Now, this tropical year is the year that our calendars measure. If our timekeeping were tied to the sidereal year, the seasons would slowly march around the calendar as Earth precessed. 13,000 years from now, summer in the northern hemisphere would be at its height in late February. By using the tropical year, we ensure that July and August will always be northern summer months. However, in 13,000 years' time, Orion will be a summer constellation. This concludes our introduction to Chapter 1. We covered sections 1.1 through 1.6. Make sure when you're studying your book that you understand scientific notation, distances, angles, and sizes in astronomy. These are very important fundamental concepts, and you need to become familiar with them now. Make sure you log into Mastering Astronomy, and I provided the link on the bottom. And once you do, you need to choose the following course, Summer Ast 180 Nichols. Again, we are covering 16 chapters in this course. Therefore, there will be 16 assignments total and 16 quizzes. I have divided each chapter into 2 lectures, so you should be able to access 32 lectures, either in the PDF format where you can read them, or in an MP4 format where you can listen to them. However, the summary lectures I am providing are optional. All the information that you need and that you will be tested in this course is included in your Astronomy Today textbook. This concludes part 1 of Chapter 1.